Okay, it's time to discuss the second rule for derivatives, and this is what we call the chain rule. Now, the chain rule has to do with when we have a function inside of another function. And so a lot of the time, you're going to be using multiple derivative rules for a single question, and the chain rule is one that you use pretty much in all of them. So let's look at what the actual rule says, and then we'll kind of talk about what's going on. So if you want to take the derivative of h at g at x, or h of g of x, what you have to do is take the derivative of g at x, and you have to multiply it by the derivative of h at g of x. Now notice I'm using these little prime symbols to denote that I'm doing the derivative rather than saying d over dx for each of these. You could use that as well, but just to keep things a little bit simple, I like to use the prime. It keeps things looking a little bit less busy. Even though it's a little more informal, I think that's okay. So what does this all mean? Well, it means that if you have a function inside of a function, what you have to do first is take the derivative of that inside part, slap it on the front, and multiply it by the derivative of the outside part, with that inside function still in there. So this can be a lot, right? This can be a lot to digest. So if you're not following this, don't worry about it. I'm going to show you an example, okay? Let's say we have f of x is equal to bracket x squared plus 3x to the 4 to the exponent 5. Now, this fits the criteria for having to use the chain rule, because if you look at the outside of this thing, if you look at it most generally, what it is it's something, right? This bracket here is something to the exponent 5. And before we said that when you have something to an exponent that's a number, it's a power rule, right? And this is a power rule. But the thing that's on the inside of the bracket, right, the base of this exponent, it's not simply x. It's something more complex than x. It's something more complicated. And because of that, we have to account for it. We have to do something to account for that, and that's where the chain rule comes in. So if I want to take the derivative of this thing, what I do first is I look at the inside, right? This function within the function, and I take the derivative of that first. That's what this g of x is, g prime of x. And I'll put it in a bracket just to keep things organized. What's the derivative of this inside part? Well, you do one term at a time, right? It would be 2x, bring down the 2, decrease the exponent by 1, plus 4 times 3 is 12, x to the 3, right? Bring down the exponent, decrease that exponent by 1. So that's the derivative of the inside of this function. Now, we have to multiply that by the derivative of the outside part, right? And what that means is we have to multiply by the derivative of this whole thing using the power rule. So this is something to the exponent of 5. So we bring down the 5 to the front. The base doesn't change. The base stays the same, just like when we do a power rule. And the exponent decreases by 1. So initially, if you're looking at this and you think, oh, I want to derive it, I'm just going to use the power rule. Bring down the 5 to the front, change that 5 to a 4, boom, I'm all done. That's this portion of the answer. But you'd be missing this portion of the answer over here. Again, you only have to figure that out, add that first part, because the base is not simply x the way it is in a normal power rule. It's something more complicated. So we have to multiply the answer you would normally get by the derivative of that inside part. That is the essence of the chain rule. And that's what we're going to do for all these questions. So I'll give you another one here. Let's say that we have 2x to the 3 minus 5x squared. And I'm going to make that to the exponent 2. And this will be f of x. And let's say we want to find the derivative of f of x. Well, you can start with the inside. 3 times 2 is 6x, and you'll have the exponent 2. That's the derivative of this first part. Minus 2 times 5 is negative 10x to the exponent 1, which we don't have to write. So that's the derivative of the inside. We multiply that by the derivative of the outside function. So we bring down the 2 to the front, multiplied by, base doesn't change, 2x cubed minus 5x squared, and the exponent decreases to 1. Now if you'd like to make your answer nice and clean, you can move the coefficient of 2 to the front, right? You can say 2 times, and then 6x squared minus 10x, 2x cubed minus 5x squared. And if you wish, you could even expand all of this and have a nice big polynomial for your final answer. That's okay as well. You're not always going to be asked to do that, so read the question carefully. But at this point, I think this is sufficient. Now, let's say that was part A of this question, right? Part A was to figure out what the derivative of the function is. Now, let's say for part B, they wanted to know what the instantaneous rate of change is of the function at a value of x is equal to 2. Again, instantaneous rate of change of this original function up here when x is equal to 2. In other words, if I draw this out, and I don't know what this looks like, it might be something like that, lots of curves, right? And let's just say here's your xy axes. At an x value of 2, right there, what's the instantaneous rate of change? What's the slope of that tangent line? That is what we're looking for. Now that's very difficult to find if you're just looking at this, right? And you want to estimate it or sketch it out. That's a big process. Probably aren't able to do it. And so all you have to do is take the derivative like we've done and then plug in an x value of 2. So we can do f prime of 2 is equal to, and we'll write out this equation, but we'll plug 2 in for x. So you have 2 times 6. Instead of x, we're going to have 2 squared minus 10 times 2 multiplied by 2 times 2 to the 3 minus 5 times 2 squared, just like that. You can then calculate all of this, and it will tell you what that instantaneous rate of change is. And the answer I get when I do this is negative 32. Now, that sketch I did previously is obviously very rough, and it was just a guess. It probably doesn't actually reflect what's going on here, but you can see that there is a negative slope at that point, and that's basically what this would look like, right? We got a value of negative 32. Negative 32 is quite steep, so it might be more similar to like a point here where that tangent line is very, very, very steep like that. It's actually kind of tricky to sketch a tangent line accurately, but you get the idea, right? So at that point, we're decreasing very, very quickly on this curve. Okay, so that's the chain rule, and I've only shown you so far the chain rule with the power rule, right? We've only applied the chain rule in a situation now where we've been using the power rule, and that's okay. But as we start to look at the other rules, we'll remember that the chain rule can still come into effect. So for the future videos, I'll show you some examples using that rule, but I'll also show you some examples where we have to incorporate the chain rule. So if you have more questions about the chain rule, watch the next few videos in this playlist as well.